Hi, this is Dr. Nick with the ECG Academy. On to Section 3, Chapter 2, talking about cardiac action potentials. And okay, so this was a dirty trick to get your attention. But we're going to talk about membranes and permeability and diffusion. And you have to think about membranes as being as having little tiny holes in them that lets things pass across. Well, all right, let's get rid of that and get more serious. The whole idea of diffusion, just to get this in the open, is if you have a material, whether it be a gas or something like that, and it's in the air, it'll eventually kind of move in different directions until this gas or whatever it happens to be, the concentration of it is equal through the whole room. Just imagine if you open a can of paint on one side of the room, eventually you can smell it all through the room. And that's because the molecules of paint are diffusing through the air. Well, what if we put something in the way, okay? Not a wall, but something that lets some things through. And the best idea of an example is something called a membrane, which is a sheet of material that allows certain things to pass through. Think of cheesecloth, lets water through, but catches little pieces of the curds of cheese. But we're talking on the order of like molecules or even atoms that can pass through. So imagine a sort of a beaker, and dividing this beaker in half, you have this sheet of material, whether it be plastic or whatever, and this sheet of material is permeable, meaning that it allows things to pass through it, okay? And now you sort of pour water on both sides of this beaker so that the water is in contact with this. Now, if you put a substance on one side, let's say, for example, salt, sodium chloride, you put salt on one side, it dissolves, and then the sodium breaks apart from the chloride because, they tend to do that in solution when they mix it with water. Now, the sodium, and if this is just a plain old membrane, there's lots of different examples, but I'm not going to get too complex. What happens is you've got all this sodium on one side, and what happens is that the force of the concentration here actually pushes sodium through this membrane, and eventually the sodium winds up on this side. And the force is kind of proportional to the concentration. So the higher the concentration, the more force to push these sodium ions through the little tiny pores in this membrane. Eventually what happens is the sodium on both sides is equal, and then sort of there is still movement back and forth, but the net movement or the total movement doesn't change, but the sodium concentration stays the same on both sides. Okay, so that's the easiest idea of the simplest concept of diffusion across a membrane. But the thing is, when you talk about cells, cells have a membrane around them. We call it the cell membrane. The cell membrane, however, is a very complex organ. It's not just a thin sheet of plastic. It's very got a lot of things going on in it. And in a later lesson in the advanced course, I'll talk about what actually makes up this membrane. But think of it as far as it's not really permeable, or it does not allow sodium and potassium ions and stuff to pass through very easily, except that there are special proteins floating in this membrane that act like pores or gates that can open and close and let substances through from outside to inside. Now, remember I told you that there's lots and lots of sodium outside, but just a little bit of sodium inside. Now, you would think that all this high concentration of sodium would apply this tremendous force and would push the sodium through the membrane until the concentration is equalized. And there's some of that going on, but the cell has special proteins that actually pump sodium against this concentration gradient, we call it, with the high concentration outside and the low on the inside. It actually uses energy to pump sodium out to maintain this high sodium on the outside and low sodium on the inside. And at the same time, potassium gets pumped into the cell so that it maintains this high concentration of potassium inside the cell. And the cell uses energy to do that. That's why you need energy to run and to jump. because all your muscles use energy to carry on their normal cellular activity. But think of this high concentration of sodium as being this potential for energy that could be delivered as the sodium rushes through. It's almost like setting the spring on a mousetrap and getting it ready to snap. Because what happens under the right circumstances is that these gates on the surface, there's a couple of other different kinds. There's a what's called a voltage dependent sodium gate that has a sort of two doors. And then there are potassium channels that are time dependent and also voltage dependent to some degree. And without getting too complicated, what happens under the right circumstances is that the sodium gate opens up, and sodium is able to rush into the cell down the concentration gradient. So it's easy for the sodium to rush in because there's very little inside and there's lots outside. So sodium rushes in, and what happens is all these positive ions make the inside of the cell more positive for a split second. But then just a moment later, these potassium channels open and the potassium rushes back out of the cell and sort of restores the normal voltage across this membrane. Well, how do we know this, and what does it look like? Well, experiments were done using a special kind of a thin tube, a glass tube, that was inserted through the cell membrane without killing the cell. And this tube was open, and it had some, material that allowed it to conduct electrical impulses. It had it was like a wire, but had liquid in here, like a salt bath. And then the end of this tube was connected to a voltmeter, and then the other end was on the outside of the cell. And so you could measure what the inside of the cell, what kind of voltage was in the inside compared with the outside. And it turned out that the inside of the normal heart muscle cells have a negative charge on the inside, that the inside is like got more electrons than protons. It's got more negative than it has positive. In fact, the voltage across this membrane is somewhere about 90 millivolts or 90 thousandths of a volt. And if we display that sort of on a screen, if this is sort of 0 volts, it lives down here around minus 90. That's sort of the resting membrane voltage gradient. We call it the potential, or transmembrane potential, about minus 90 millivolts. Okay, so now what happens when the cell is ready to fire? Okay, what usually tips the cell to firing is that the cell on the inside becomes a little bit more positive. It reaches a certain threshold voltage, we call it, which may be minus 80, something like that for certain cells. Once it reaches that threshold, suddenly these sodium gates open, and sodium is able to rush into the cell, making the inside of the cell much more positive than it was before. So this membrane gradient, this voltage across the membrane that we're measuring here with the voltmeter, it suddenly becomes positive. It goes up above 0, and it stays there for a split second until finally what happens is the potassium gates open up, and potassium rushes out of the cell, bringing all these positive ions out and restoring the normal resting gradient of about minus 90 millivolts. Okay, so this sequence of becoming more positive, sort of reversing the negative polarity across this membrane, we call it depolarization. Depolarization is the changing from negative to positive on the inside of the cell, and then a split second later, when potassium rushes out of the cell membrane becomes repolarized. So you have this. So repolarization is the sequence, is the part where the potassium rushes out and the normal resting membrane potential is restored. Now imagine what happens to the next cell over. So the next cell here is, remember, the cells are connected by this intercalated disc, and that disc is able to pass ions across. So now when this cell depolarizes and you have all these positive charges on the inside, the sodium rushes in, the positivity can pass from one cell to the other. And then what did I say? If the inside of the cell becomes more positive, this cell will reach its threshold. Okay, if this is 0 millivolts, this cell reaches its threshold of minus 80 millivolts or whatever, and this cell fires. And then you get an action potential of the next cell, and the next cell, and the next cell. So that's how cells are able to pass the signal from one to another through this very complicated movement of ions in and out of the cell membrane. Now, it's this positivity that moving in space, this electrical positivity moving from one cell to another through the heart, that is what we're able to pick up and amplify and put on paper as the electrocardiogram. So on the next video, what we're going to do is talk about the heart muscle itself, and when those cells depolarize and repolarize, what does the signal look like when we pick it up from the surface? So thanks for watching. This is Dr. Nick from the ECG Academy. Stay tuned for the next recording.